Okay, so for our next one, what if we have f of x is equal to negative 2x minus 1? How do we take the derivative of this guy? Well, notice that we have two terms and they're basically added together, even though there's a negative sign here. This could be negative 1, so you could say these are both summed together. So we know we're going to take the derivative of each part separately. So the derivative of the first part, we have to do a little bit of thinking about here. So let's go f prime of x. What do we have? Negative 2x. So if we go over here, this is a constant times a function. The function being x, the constant being the negative 2 out in front. So the way we handle it is just like it says here. We just take the constant out in front and then we take the derivative of the function. So really, in practice, when you have negative 2x, the negative 2 is sitting out in front. It just stays out in front. Now we have to take the derivative of x, which we did just a minute ago. So it's really x to the first power. So a 1 comes down because of the first power, x, and then for the new exponent, it's 1 minus 1, right? Because we just take 1 off the exponent. So that really and truly takes care of this first term. The negative 2 stays out in front. The derivative of this is 1 times x to the 1 minus 1. Okay? Now what about this guy over here? What's the derivative of negative 1? Well, negative 1 is a constant. The derivative of any constant is always 0. So over here, we always have a 0. So what we have here is two functions summed together. The first one is the negative 2x. The second one is the negative 1. The derivative of the first one we wrote down over there. The derivative of the second one is just a constant, so it's 0. So I'm writing 0 here so you know what I'm doing, but really after you do enough derivatives, you'll know that the derivative of that constant just disappears and it doesn't even play. So finally, the answer that we would write would be this guy, negative 2, and then we have x to the 0 power, which is just 1. So the answer is just simply going to be negative 2. So when you think about it, though, you know, I'll take a little chance to show you an aside. What is this a graph of? If you plot this, negative 2x plus 1, this is just a line, right? You have a slope here, right? And you have, you know, some y-intercept there we could draw and plot. But the point is it's a straight line with a slope of what? What should be the slope of this line? If this were just y equals some line, you plot it, what should the slope be? It's negative 2 because that slope is always in front of the variable. So the slope of this line never changes because it goes on and on forever with a slope negative 2. Look at what we calculated for our derivative. It's a constant, negative 2, always. No matter where I'm looking at on this coordinate plane, no matter where I look, the slope of the original function is always negative 2, which makes total sense for a line because the slope of a line never ever changes. Unlike that parabola, the slope of that parabola does change all the time. So you can kind of do a little bit of a sanity check to make sure that you're getting something that kind of makes sense. Okay, let's go and work another one. Let's say that we have f of x is equal to 1 minus x squared. 1 minus x squared. So again, we have two functions, and they're basically summed together. The fact that this is negative doesn't really matter because you could say 1 plus negative x squared. But they're summed together. So just like we look at our guy here, we take the derivative of the first part, we take the derivative of the second part, and we basically add them together. But the first part we have is just a constant, so the derivative of that is 0. What is the derivative of this part here? So we take the exponent, move it down, so we have a minus 2. You have to keep the minus sign because you have a minus sign here. 2 comes down, x goes there, and then the exponent is going to be 2 minus 1 because we always subtract 1 off of the exponent. So this derivative, f prime of x, is just going to be equal to negative 2x. So that derivative is negative 2x. The derivative of the first part was 0. Derivative of the second part was this, negative 2x to the first power, and that's it. And with practice, this will just become very, very simple for you. Now, occasionally in the books or in your exams, your professor might give you something like this, 1 over 2x. And say, hey, take the derivative of that. And you might look at that and say, well, he has not told us how to handle derivatives like this. I have no idea how to do this. Well, in fact, you do know how to do this. But just like in algebra, just like in calculus, a lot of times you'll need to kind of massage whatever you're given into a form that you already know how to solve. If you can do that, then you've basically reduced the problem down to something you already know how to do. So how would you do that? My advice to you, and I do this myself, I have years and years of experience with calculus, but every time I see something like this, I always do the following thing because it helps me. I rewrite the function, right? I rewrite the function like this. I rewrite it as 1/2 times x to the negative 1 power, right? Think about that. The 1/2 is sitting out there. The 1 over x is rewritten as x to the negative 1 power, right? When you write it like this, it's really easy to work with because we know how to take the derivative of these x to the power of yada yada terms. The fact that there's a constant out front is absolutely no problem because if we have a constant times a function, we just stick the constant out in front, take the derivative of what's left over. So we already know how to do that, even though this looks a whole lot more difficult. So the derivative is going to be, the 1/2 is just going to stay out front, and then we take the derivative of this. Now you do have to be careful, but I will tell you that it does follow the exact rule, but you do have to be careful because negative exponent can kind of get a little tricky if you're not careful. The negative 1 does come down, so you have negative 1, and then you write x, and then the exponent you have to subtract 1, but you have negative 1 minus 1. This is exactly what we've been doing before, where we took the exponent and subtracted 1. Well, here we're taking the exponent and subtracting 1. Only difference is my exponent is already negative, right? But I'm doing exactly the same thing. So the derivative is going to equal, with this negative, it's going to be negative 1/2 times x to the negative 2. And that is the answer. I mean, absolutely, that's the answer. You could circle that, and I actually would circle it this way. But since your original problem was written like this, you could be courteous, if you wanted to, and rewrite it in that form. Negative 1 over 2x squared. And make sure that you understand that this is exactly the same thing. The 1 over, the 2 is in the bottom, the x to the negative 2 goes into the denominator, making it a positive exponent. So what we have here is correct. You could totally stop here. This is absolutely correct too. There's nothing wrong with that. Just depends on how you prefer to see it. Now, as you get more comfortable with derivatives, you might start from this and be able to take this derivative no problem and just end up in this final answer. My advice to you, though, is don't try to do that. Make it easy on your brain. Why make things more complicated? Just convert this to something you already know how to deal with. And then, you have to deal with the negative exponent, but then you can go back in the end if you want. If you try to go straight from here to here, you'll probably miss this negative sign or you'll miss something else. So keep it simple is really my motto. Okay, the next problem is going to be, what if we have f of x is equal to x to the 2/3 power? So we have a fractional exponent, but I told you it doesn't matter what the exponent is. It could be 1.9, it could be negative 17 halves. It doesn't matter. You do exactly the same thing. So we take the derivative and we just take this exponent and we write it out in front, 2/3. Then we write x down, and then we have to subtract 1. So we write 2/3 minus 1. And that's going to end up being the answer. Now, a lot of you probably could look at 2/3 minus 1 and get the answer. No problem. But, for some of us, we have to do a little bit of something on paper to make sure we don't screw that up. So we put 2/3 here, subtract. Now I'm subtracting 1. The easiest way to do this is make it 3/3. So I have a common denominator here. So f prime of x is going to be 2/3 x. What are we going to have here? 2 minus 3 is negative 1, negative 1/3. Okay, so 2/3 times x to the negative 1/3 power. Again, a lot of you guys could start here and realize that the answer is going to be negative 1/3. That's okay. This step I do myself all the time because when dealing with fractions, it's just so easy to screw something up. What if this weren't 2/3? What if it was 5/17 minus 1? Okay, then maybe you have to think a little more. So just write it as 17 over 17 so that you can easily subtract those fractions and you never make a mistake. The other thing is, if you write all your steps out like this on your exam, if you do happen to make a problem, you can get most of the credit for the problem if it's clear what you were trying to do. If you skip steps like this, like a lot of people might just start here and just go straight to the answer because they can do it in their head. 2/3 x to the minus 1/3. Okay, great. But if you actually happen to make a mistake, then I'm not going to give you much credit for this because I won't know what you're doing. But if you write it all out, I can see that you knew what you were doing, and everybody can make a sign error occasionally, so you're in better off shape. Okay, and just to sort of introduce our new notation, or our different notation, you could also say that df with respect to x is 2/3 times x to the negative 1/3. Exactly the same thing. No difference. F prime of x, df dx, same exact thing. Just a different way of writing it. Okay, let's switch colors and go to, what if we have f of x is equal to x to the 3 halves. So same sort of problem, just a different fraction up there. We're going to do the same thing. F prime of x is equal to, take the exponent down, 3 halves, okay? Mark the x, and then the exponent's going to be 3 halves minus 1. And again, a lot of you guys can do this in your head, that's okay. So we'll have 3 halves x. What is this going to be? It's going to be 3 halves minus 2/2 to get a common denominator here. All right, so f prime of x is going to be equal to 3 halves x. 3 minus 2 is 1, so 1/2. 3 halves x to the 1/2, which is exactly the same way if we write it differently. df dx is equal to 3 halves x to the 1/2. Exactly the same thing. So we can write it both ways. And so it's the same sort of thing. You're subtracting the guy off. A lot of you guys could probably go straight from here to here and do it. That's fine. It's really up to you. But the more steps you show, I'm telling you, it's a matter of time before you make a mistake on your exam, and then you'll wish that you had shown all of the work. All right, let's go ahead and do another problem. Let's say we have f of x is equal to negative 4x cubed. Negative 4x cubed. So here we have sort of the same thing. We have a constant right out in front of our function x cubed. So all we do is we say f prime of x is we basically keep this out in front. So this negative 4 stays out in front because and then we take the derivative of the x cubed, which is we take 3 down in front, so it's going to end up being multiplied, times x. 3 minus 1 is 2. And I think most people are pretty safe to put 3 minus 1 and just put the 2 down there. But look what we have here. 4 times 3 is 12. So f prime of x is equal to negative 12x squared. Negative 12x squared, and that's the final answer. Okay, the next problem, let's say, is f of x is equal to, we're getting a little more complicated each time. Let's say we have 3x squared minus 4x plus 2. So notice what we have. This is a polynomial, right? And I kind of alluded to this before, but notice it's really the sum of 3 things. Anytime you have 3 things added together, we're trying to take the derivative of the whole thing. You just take the derivative of each part separately, and basically you're just adding up the answer. So it's very, very simple to do because of that. So instead of writing f prime, we'll just get practice with the other notation. df with respect to x, the derivative, the rate of change of the function with respect to x is equal to the following. How do you handle the first term? Well, they have a 3 out in front, so it stays out in front, 3 times the 2 from the exponent that drops down, and then in the exponent you have 2 minus 1 giving us the 1. So this is basically done. Here you have this negative 4 sitting out in front, so it just sits out in front here. But really, if you want to write it all out, you would say, okay, well, I'm multiplying by the 1 that's in this exponent. X to the 1 minus 1 is 0. So that's basically going to end up disappearing. Plus, what is the derivative of any constant? Derivative of any constant is 0. So I've basically done all the work. The answer, df, with respect to x, is going to equal 6x. And then here, this is x to the 0 is 1, so you have negative 4, and 0 just stays out. So df dx is 6x minus 4. Make sure you understand that. The 3 stays out in front, 2 drops down, x to the 1 power, because 2 minus 1, okay? Negative 4 stays out front, 1 drops down, x to the 1 minus 1 is 0. So this is going to end up dropping out too. Now over time, as you get more comfortable, you won't really need to write all this stuff down because you'll realize that anytime you have a number in front of x, it's just going to be the number is going to be the final guy there. The x is going to disappear. And then finally you have the derivative of this is 0. I'm showing everything because I want you to truly understand it all. As time goes on, you'll find your own comfort level with what you want to show. F of x let's say, is negative 2 x cubed plus 6x squared minus 5x plus the square root of 2. So again, another polynomial. This is added to this, is added to this, is added to this. So I take the derivative of each thing separately, and I'm just adding up the answer. So df with respect to x, the derivative of the function, the slope of the function with respect to x, right, is, and what we're going to have here, the negative 2 is going to stay out front, multiplied by my exponent, which drops down, which is 3. And then I write my variable. My new exponent is 3 minus 1, which is 2. Okay? And then, over here, the 6 stays out front. The 2 drops down. I write my variable. My new exponent, 2 minus 1, is 1. And then here, I'm going to have the 5 stays out front. The 1 drops down from here. X to the 1 minus 1 is 0. And that's basically how that's going to go. This is going to end up falling away in a minute. And then the final part, square root of 2. Square root of 2 is just a number. Don't worry about the fact that it's a square root of something. It's just a number. It's a constant. So the derivative of any constant is 0. And so here's my derivative. df with respect to x is equal to negative 2 times 3 is negative 6x squared plus 12x minus 5. The 1, of course, is just a 1, so it falls away. X to the 0 is 1, so it falls away. So all I have left there is the negative 5. So this is the answer. And actually, as you get more comfortable with derivatives, you don't probably have to show all these intermediate multiplications. You could just look at this and say, well, 2 times 3 is 6. Okay, there's that. The new exponent is a 2. Okay, this guy, 2 times 6 is 12. There's that. The new exponent is 1. The derivative of this is going to be negative 5. Derivative of this is going to be 0. So really going from first step to third step is probably okay when you're taking a relatively simple derivative like this. I'm showing it all for you so you truly understand where I'm getting everything. All right, so let's go and do something a little more, not too challenging, but a little more challenging. What if I have f of t, so it's a function of time this time, is 7 times t to the negative 5. Well, don't worry about the fact that it's t. That has nothing to do with it. All right? It's going to be done exactly the same way. This exponent should not scare you because the rule that we apply for these guys applies if it's negative or positive exponent. So the derivative of f with respect to what? T this time, because it's a function of time. The change of the function with respect to time is the 7 stays out in front times the exponent. You drop down, negative 5. Then you write your variable down, and then your new exponent is you take the original one, you subtract 1 off. So you're just doing the same thing. You're dropping the exponent down, your new exponent is just subtracting 1. So df dt is equal to negative 35 times t to the what? To the negative 6. Negative 35t to the negative 6. Not that bad, because it's written in terms of this exponent that you already know how to deal with. But the next problem could trip some people up. F of t is equal to negative 4 over t to the 9. So this is the kind of thing on a test where if you haven't practiced it, you'd look at this and you'd be like, well, I don't know how to do that. I know how to do it when they're up here in the top, but I don't know how to do it when they're in the denominator. Well, we've talked about this. Just rewrite the function. Rewrite it in a form that you know how to deal with. As long as you're legal, you can do this anything you want to this function. So we'll call it negative 4 times t to the negative 9th. And make sure you completely agree that that is exactly the same as the original function. We just stuck a negative on the exponent there. And we know how to take a derivative of this guy. So let's go f prime of t, take a derivative, is equal to negative 4 times negative 9 from the exponent that drops down, times t to the negative 9 minus 1. We subtract off of the exponent. Same rule as before. So f prime of t is equal to 9 times 4 is 36, negative times negative is positive, so 36 times t to the negative 10. And you can leave it like that. That's absolutely fine to do. But since the original problem wrote it like this, you might want to be a little courteous, let's say, and just write it as 36 over t to the 10th power. 36 over t to the 10th power. That's the answer. This is the answer also. It's totally fine to leave it like this. If you want to write it in terms of how the original problem was, you would put the guy in the bottom. So I hope you see that some of these problems look quite different from each other, you know? I give you a few rules, and then when you start adding things together, putting exponents on the bottom, it looks different. But once you learn these rules of derivatives, you'll learn that they're really all done in the same way, okay? So let's go on and do a few more, just building our skills. What if we have f of t again, let's say, negative 3t squared plus 3 over t to the 6th. So here we have a combination of two different things. So we're going to take the derivative of this guy and then the derivative of this guy separately and add them together. This looks a little funny, but we know how to handle that. We're just going to rewrite it. So I would suggest to you that if you're given something like this, you rewrite it as negative 3t squared plus 3t to the negative 6. We rewrite it like that because now you have, it in the form that we've sort of been working with a variable raised to a power. And they're all, nothing's in a denominator like that. Okay, so we'll take the derivative. What's the derivative of this guy here? You'll have the negative 3 here times the 2 from the exponent. Then you write your variable, and then 2 minus 1 is going to be 1, so I'm going to leave it like this. Plus, you'll have 3 out in front from the second term, negative 6 from the exponent. Then you write your t down, and then you'll have negative 6 minus 1 in your new exponent. So finally, f prime of t is going to equal, this guy is going to be negative 6t, this guy, negative 18t to the negative 7, right? To the negative 7. And I can rewrite this term if I want to be, match it to how my original problem was written. So I would say negative 6t minus 18 over t to the positive 7th power. And I don't have to do this. I could totally leave it like this. So the answer I'm going to get is going to be negative 6t minus 18 over t to the power of 7. Okay, let's switch colors a little bit and do a few more, working up our complexity a little bit each time. What if I have y is equal to the square root of 5 times x? So you might look at this and say, well, I've got a square root, I've got a 5 times an x, and I've definitely never seen anything like this before. But what you really need to do is rewrite it just like anything else. So just see if you can always figure out a way to rewrite these things. You can rewrite this as the square root of 5 times the square root of x. You think about it because you can just multiply these things under the radical. So now what you have is a constant. This is simply a number. Square root of 5 is just a number. This is a function. So we just take this guy and do it like we've always been doing. So dy with respect to x is equal to, the constant sits out in the front, and then we take the derivative of this guy. But what is this? I can rewrite this further and say square root of 5 times x to the 1/2, because that's what a square root is. So I multiply this by the exponent, 1/2, and then my variable, and then up here I'm going to have 1/2 minus 1. I'm going to subtract 1 from my new guy. So what I'm going to have is dy, derivative of y with respect to x, is going to be the square root of 5 over 2 from this, times x. 1/2 minus 1, I think most people can figure out in their head, is probably just negative 1/2. And if that confuses you, put 2 over 2 and then do your fraction subtraction there and get the answer there. So you can leave this as the answer. That's absolutely no problem. You can also rewrite it as y prime is equal to square root of 5 over 2 times the square root of x. Because you move this guy to the bottom, you'll have x to the positive 1/2, which is just a square root. So you can even simplify this more if you want. Any of these answers is correct. Square root of 5 over 2 times x to the negative 1/2, or you can rewrite it as this guy. That's fine as well. So, the trick here is, with derivatives, is once you learn all the rules, they're all really done in similar fashion. Just see if you can rewrite one of them sometimes, because that could be the trick that you might need. So for the next guy, what we want to do is I want to find the derivative of the function, but evaluate that derivative at some number that's given. All right, so for our first problem, I have f of x equals negative 7 over x to the power of 9. And I want to evaluate the derivative at a is equal to 1. So when you see this kind of thing, first of all, just ignore this. Find the derivative of your function. So f prime of x, right? First thing is going to help us here is rewrite this guy. F of x is equal to negative 7x to the negative 9. Just move it up to the top like we've been doing. After that, it'll just be negative 7 times the exponent, which is negative 9, times my variable. And then my new exponent is negative 9 minus 1, which is negative 10. So I'm subtracting 1 off of that exponent. So my derivative is simply 9 times 7 is 63, so it's positive here. Negative times negative is positive. 63x to the negative 10th power. 63 times x to the negative 10th power. So here's the derivative. This derivative represents the slope of my original function at any value of x I want to look at. Any value of the function. I just put a value in, I get the slope of my original guy. Here I want to know what is the slope when I say a here, but really it's x is equal to 1. So all you do is put it in there. F prime of 1 is equal to 63 times 1 to the negative 10th power. So 1 to the negative 10 is just going to be 1, right? So the answer that you get, evaluated at a is equal to 1 or x is equal to 1, is 63. What this represents is, if you were to plot it, is that if I plot my original function and I look at x is equal to 1, go up to my function and draw that tangent line, the slope of that tangent line at that point is going to be 63. I take the derivative, I evaluate it at whatever point I want, and I get back an actual number that's just representing the slope of my original curve at that point. So to illustrate that further, we'll just do another one like that. F of x is equal to 1 over pi times 3x squared minus 4x. And I want to do that at a is equal to 2. Let's do it at a is equal to negative 2 actually. Okay? So here's a function. How do I take the derivative of this function? Well, there's a couple ways to proceed, but when you really think about it, if you consider this a giant function, I have a constant sitting out in front. So basically that constant continues to stay out front. And then on the inside, I just take the derivative of everything that's in there because they're just added together. So here I have, on the inside, I have 3 times 2, because of this multiplication, times x to the 2 minus 1, which is 1. So I subtract 1 off the exponent. And here I have 4, and then what I'm going to have here, the 1, the exponent from the 1 comes down, times x to the 0 power. Because 1 minus 1 is 0, subtracting 1 off of that exponent. So f prime of x is equal to 1 over pi times, 3 times 2 is 6, so I have 6x minus 4. And that's basically the derivative, 6x minus 4. Okay? And so all I need to do at this point, this is the derivative that expresses the slope of my original function at any value I want, but I'm interested at x is equal, or in this case I just label it a is equal to negative 2. So I just put that in there. So I'll switch colors for that, and I'll say f prime at negative 2 is equal to 1 over pi times, we'll do it 6 times negative 2 minus 4. Okay, which is equal to 1 over pi times, what is 6 times negative 2? That's negative 12 minus 4, like this. And so f prime of negative 2 is equal to, what I'm going to have here is 1 over pi, and inside here I'm going to have negative 12 minus 4, which is negative 16. Right? So finally, if I want to write my answer down perfectly, f prime evaluated at negative 2 is equal to negative 16 over pi. And this is the final answer. So basically all we do, if you're asked to evaluate a derivative at a given point, is you calculate its derivative just like we've been doing, and you just take the value and you plug it in. So what this means is that if I look at my original curve, if I plot it, if I look over at x is equal to negative 2, and I go up to that curve and draw that tangent line at that moment, I'm going to get a slope that I can measure. That slope is going to be equal to this number here exactly. And that's what the derivative is. So the derivative, just to wrap it up here, is a general concept. It says I have a function This function has a slope that's constantly changing because it's squiggly, unless it's a straight line, right? The derivative is a new function that I derive from my first one. The new function represents the slope of the original function at any point I want. And if I want to actually capture that slope and look at it, I can plot it and figure it out, but I can also evaluate my derivative at any point I want, and I will get back a slope that represents the slope of the line tangent to the original curve. So I didn't talk about deriving a derivative in terms of a limit. You can look in the Calculus 1 tutor separate DVD course for that. Didn't talk about some of those things, but we did give a good introduction to what a derivative is, practically speaking, in terms of the graphs that we drew. We represented the simple derivative methods here, where we have a x raised to a power, derivative of a constant, sum of two different functions that are added together, taking the derivative. But you can see that even those simple little rules, when you combine them into more complicated functions, really allow you to take derivatives of more complicated things. Now, as we go into the other sections in the future, we'll introduce new methods and new classes of things to look at and know how to take derivatives of, so that you'll build your skills one thing at a time, and then by the time you get to the end of it, you'll be able to look at any function and take the derivative of it because your skills will be so strong. So definitely practice the problems in your textbook. Practice, practice, practice. Watch this section again. Work these derivatives again if you think that'll help. Most people it will help. Go and work a lot of problems, and I guarantee you with this guy, you'll do very, very well on your exams and on your homework.